We're going to explore electron configurations a little bit more. And to do that, we're going to consider the electron configurations for two different atoms, oxygen with 8 electrons and sulfur with 16. You can split these configurations into two different sections. You can split them into core electrons or valence electrons. And these are also known as inner shell or outer shell electrons. Inner shell electrons or core electrons are just those electrons that exist in orbitals with smaller n values. And outer shell or valence electrons are just the electrons that exist in the orbitals with the biggest n value. So for oxygen, the largest n value is 2, the 2s orbital and the 2p orbitals. If you wanted, you could draw a dividing line between the valence shell, the n equals 2 shell, and the core shell, which in this case is the n equals 1 shell. And you could do something similar for sulfur. Sulfur's largest n value is 3, so the n equals 3 shell is the valence shell, and n equals 1 and n equals 2 represent the core shell or inner shell. And something worth noting here is that the valence part of each configuration looks pretty similar. And that's not a coincidence. If you look at the periodic table, you'll find out that oxygen and sulfur have a lot in common. Both of them are in the same group, which means they're going to have similar bonding, similar chemical properties, and things like that. And it turns out that the valence electrons are the ones that are involved in the bonding, and they typically dictate the behavior of those atoms. So any set of atoms that belong to the same group are going to have the same valence configuration. The number of core electrons can be different, but the number of valence electrons are going to be the same within a group. And it's possible to link these electron configurations to the position on the periodic table as well. This might not look like the normal representation of the periodic table that you're used to, but it's actually in a lot of ways better than the one you're used to. When you arrange the periodic table this way, the relationship between the electron configurations and the structure of the periodic table become a little bit more clear. The table is broken into blocks of elements. So you would have an S block, an F block, a D block, and a P block. And any element that shows up in an S block, for example, is going to have its valence electrons in the valence s orbital. Anything in the F block will have valence electrons in the valence f orbital, and the D block will have its final valence electrons in the valence D block, and the P block elements are going to have their final valence electrons in the valence P block, in the valence P subshells. So we can make this a little bit more clear by putting example elements in. So we'll look at hydrogen, and we'll look at carbon, and we'll look at titanium. So with hydrogen, you have 1 electron. So no matter where it goes, it's going to be in its valence shell because there's only 1 electron. And hydrogen is, in fact, an s block element because its only valence electron is in an s orbital. Carbon has 6 electrons, and it has the electron configuration 1s2, 2s2, 2p2. So now you have multiple different n values. You have n equals 1 and n equals 2. So you can identify that n equals 2 is the valence level. And you can identify that the final electrons in that valence level are in the p subshell. So carbon is a p block element. And titanium with 22 electrons is a d block element. And this one's a little bit stranger because even though n equals 4 is the highest n value, the 3d electrons actually come after the start of the n=4 shell. So even though we don't consider d electrons to be valence electrons, the final electrons are in that d subshell, so we call it a d block element. The other thing you might notice looking at this diagram is that each row of the periodic table corresponds with a principal quantum number. So the numbers going down the left-hand side here, 1, 2, 3, 4, 5, 6, 7, they represent the principal quantum number of the valence shell. Hydrogen, with the valence shell in the 1s orbital, belongs to row 1 with an n=1. If you look at lithium, lithium's valence electron is in the 2s orbital, and it's in the second row down. And that pattern continues. The other thing you might notice if you read from left to right across the periodic table is that reading left to right represents writing the electron configuration. Hydrogen is a 1s1 configuration, helium is a 1s2, and then the next element, lithium, is a 1s2, 2s1 configuration. When you go to beryllium, you end up with a 1s2, 2s2 configuration. And you're in the second column now. If you move to boron, which is in the same row, you have a 1s2, 2s2, 2p1 configuration. You've moved 2 elements across in the s block, 1, 2. So you've filled the 2s orbital, and now you're 1 column into the p block, and you have a p1 configuration. You can actually label across the top 1, 2, 3, 4, 5, 6, 7. And the number at the top of the periodic table that I've just written will tell you how many electrons are in the valence shell. Hydrogen has 1, beryllium has 2, boron has 3, carbon has 4, and so on. And this will be true for every row of the periodic table. If you go all the way down to row =4, potassium is going to have 1 electron in its valence shell. Calcium is going to have 2 electrons in its valence shell. And gallium is going to have 3 electrons in its valence shell, and so on. A final thing to note is that at the very far right-hand side of the periodic table, you finish the p block for a given principal quantum number. And after you fill that p block, you move on to the next s block. So if you finish the 2p subshell, the next element is going to have a valence electron in the 3s subshell. And this pattern lets us write simplified electron configurations called condensed configurations or noble gas configurations. And the way these work is that every element within a row is going to have the same core configuration. It's only going to differ in the valence configuration. Everything, for example, in the n=4 row is going to have the same core configuration. And that configuration is going to correspond to the noble gas in the row above it. This is argon. So everything in the 4th row is going to have argon's configuration. We can demonstrate that by looking at potassium, calcium, and scandium. Everything in this row has the same core configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and that's the configuration for argon. So one way that you can write a simplified version of the configurations is to write just the name of the noble gas in the row before it. So for potassium, you could simply write the electron configuration as argon with a 4s1 electron, or calcium as argon with 2 4s electrons, or scandium as argon with 2 4s electrons and a 3d electron. And this is particularly useful for very, very heavy atoms. So it's not super useful if you're working with, a second row element or something. But if you look at, say, iridium, if, for example, you look at something like iridium that has lots and lots and lots of electrons, if you had to write out a full configuration, it would take you a long time. Using a condensed version is much faster. The other thing that condensed configurations do is they put the focus on the valence shell, which is where most of the bonding and properties come from anyway.